Looking at this topic, series and parallel connection of capacitors. We have discussed what a capacitor is. And today we'll be looking at how these capacitors can be connected both in series and in parallel. I want to remind you that this is a circuit symbol of a capacitor. It has the positive and the negative. Please, there's a big difference between this and this. This is a circuit symbol for a cell or a battery, where the longer side denotes the positive side, this denotes the negative side or terminal. So for a capacitor, the two terminals appear to be the same, but we have the positive plate and the negative plate. So let's continue. Now, we said that a capacitor is a device that can store and discharge electrical charges. So, if these capacitors, let's look at the series connection first. Let's look at the series connection. Series connection. When you have two or three capacitors arranged side by side, this is C1, C2, C3. So, assuming these three capacitors are connected to a cell, a battery. So, since this is the series arrangement, the charges that are passing through C1, the same charge that will pass through C2, the same charge that will pass through C3. So the charges passing through the three capacitors is common or is the same. Whereas the potential difference is different. If you want to measure the potential difference of C1, it means you have to connect a voltmeter parallel to it. So the potential difference for the three will be different. Each of them you need to connect a voltmeter. Each of them you need to connect a voltmeter. So, why I'm doing this is that sometimes they will tell you that the formula for calculating the total capacitance, or what we call the effective capacitance, is 1 all over C equal to 1 over C1 plus 1 over C2, depending on the number that are connected. But I want to show you how you can derive this formula. That is why I'm explaining this. If capacitors are connected in series, the charges passing through them is the same, but the potential difference across each of them is what? Different. So from our previous class, we said that the quantity of charge in the capacitor depends on the potential difference, or directly depend on the potential difference. I will say that Q is equal to CV. We have done this. We have done this. And then from here, it means that the charge that is passing through C1 is the same. What of the potential difference? From here, if you make V the subject, V now becomes Q all over C. So it means that the potential difference for C1 will be different, for C2 will be different, for C3 to be different, which we can say that Q over C is equal to Q, because remember the charge is the same for each of them, all over C1 plus Q all over C2 plus Q all over C3. So from here, we can say that this is what we have here. We can write this as Q multiplied by 1 all over C is the same, equal to, because Q is common, so we'll factorize it, Q into 1 all over C1 plus 1 over C2 plus 1 all over C3. Remember, this is the left-hand side of the equation and this is the right-hand side. So whatever you decide to do on the left-hand side, you equally do it on the right-hand side. So since Q is common, this will take care. I will have that 1 all over C effective or equivalent will be equal to 1 over C1 plus 1 over C2 plus 1 all over C3, which is the formula for calculating the effective capacitance. For example, if the value of C1 is 2 microfarads, C2 is 3 microfarad, and C3 is 1 microfarad. So you want to know the effective or total capacitance. You simply deploy this formula by saying 1 all over C equal to 1 all over 2 plus 1 all over 3 plus 1 all over 1. Of course, we need to take LCM, which is 6 in this case. 1 into 6 is 6 times 1 is 6 plus 3 into 6 is 2 times 1. 3 into 6 is 2 times 1 is 2 plus 2 into 6 is 3 times this is 3. So this will be, if you add up this plus this is 5 plus 6, we have 11 all over 6. Therefore, we have 1 over 6 is equal to 11 all over 6. But what we are looking for is what? C. So it implies that C now will be equal to 6 all over 11 microfarad. By cross multiplying, some people will be asking, why did you get 6 C to be 6 over 11? If you now cross multiply, 1 times 6 is 6, equal to 11C. Making C the subject, you divide both sides by 11, and C will be equal to 6 all over 11. This is the series connection. Then for connection in parallel, parallel connection of capacitors. When capacitors are connected in parallel, for example, you have this. Remember, write them, they're equal. Connected to a cell. This is C1, C2, C3. So if this is point A and this is point B. The charge that is flowing from this cell, by the time it gets to here, this point, it will now split. The charge going to C1 is different. There we have Q1. The charge going to C2 is Q2, and the charge going to C3 is Q3. So remember the potential difference. If you want to calculate or read the potential difference, you need to, the potential difference, you connect a voltmeter that will, so the potential difference is the same while the charge is different. So from here we know that Q is equal to what? CV. Q is equal to CV, and we say that CV is equal to, when you look at this, we have C1, the voltage is common, we have C1 V plus C2 V plus C3 V, because the voltage is common or the potential difference is common. And this is the left hand side, this is the right hand side. So what is common here is what? V, because if you factorize this, we have CV equal to V into C1 plus C2 plus C3, where this V will take care of this. So for a parallel connection, the formula becomes C equivalent equal to C1 plus C2 plus C3. So assuming we have 3 microfarads for C1, for C2 we have 4 microfarad, and for C3 we have 1 microfarad. So for you to find the total capacitance, C equivalent will be equal to 3 plus 4 plus 1, which will give us what? If you have add this plus this is 7, that will be 8 microfarad. That will be 8 microfarad.